Hello everyone, I am Xiao Gang. Okay, let's talk about what the most complicated part of this T-map is. Actually, it's this key function. Actually, why is it not complicated to apply? Don't look at these explanations first, don't open the code. That is, if I use this struct as the key value for this T-map, as long as the re-representation of my struct, etc., operations and calculations conform to this GitHub hash, I can then determine these two keys. Are these two structures equal? And what is the number after their hash? So the problem is that many times we don't want to rely on operators like this and get hash. Why? If I in this map, I just need to know the type of this actor. They are all monsters. They are all monster, right? For example, these structures we call FNP info. We just assume that the NPC's type is one kind. We then assume that this is the K value or key value is the same, but if we are placed after, etc., actually the effects we want are including this NPC, its life points, magic points, and its same position. We want all the information to be equal. Only then do we consider these two pieces of information. They are equal in our game, but when using temp, sometimes we only need that their types to be equal. What should we do then? So we just use the equality operator or just check if all of our properties are equal. But over here, we'll pass an additional function to it. This function tells Unreal, and the engine will know the key at this point. It needs to check if this key is equal using a custom method, rather than checking for equality, using the judgment in my original struct, and then it will proceed this way. Doing it this way requires passing this definition. How should this direction, be defined? It has two type defines and three function definitions. So, first, let's not look at the code yet. First, you need to be clear on what you're describing is what data type is your K value, and what data type is this T-map. What is its value? What is the value? And how do they compare it? And how are the values in these three columns calculated? So these two type defines three input functions. These are what this work. Clearly, this kit and net type. So it is defined the value type that we pass. This element, int type, it is actually defined. The element type that is passed. So this function returns the key of the element. So we must pay attention to this. This place, the element init type of this spot, it is our tpair. Remember that, and the key of tpair is key init type, and this tpair, this is our element init type. It is tpair, and then this place outputs. It outputs two values. We will determine if these two values are equal, and then this provides a value. We will modify it based on the value of this key to calculate its three-chain value. Then remember that the map type is tpair. Correct. Next, let's look at this structure. Okay. Next, let's look at this structure. First, this structure has two strings. One is UEC, and one is 3flow. It's the specific attribute. This unique marker serves as its unique identifier. That is a rejection attribute. And then in this place, it is a displayed construction like this. It is a visible construct. That means it doesn't allow you to directly pass a float, so it digitizes it. You must write out the semi-struct to avoid some problems arising from private conversion. Okay, this is our structure. You can see it doesn't even have overloading, etc. The operator. It also didn't implement this function, jati type phc. Then it is done through the sequence that follows these two point locations and three witness functions. Obviously, this place is also a struct. So what does this structure do? If you use this structure as the K value for our T-map, so the value of our T-map might be arbitrary. So we use a template here. Then the value type of T-map is it. It's called the value type of T-map. And this structure, it inherits from our base key function. And its first parameter is our type. This is the element of our type. It is this T pair, because you know that our T-map is composed of many T pairs. Then obviously this type, the parameter passed to it beforehand, it is a my struct. And then the value type afterward can be int, can be string. It is this value, okay, no problem. And then this parameter later on is what we use for this calculation. What is the data type of the value of this key? Could you elaborate? This is the type that we use for calculating the key. It is what truly participates in the equality check, hash calculation, and comparison of our key values. It is this. And here, we define this thing as its negative class. Why don't we have this in our call? We often use super, but we didn't do this because our UBTUHT helps us with this type definition. If you put it into our color palette generation code, you will search for super. You can see. So this one, for the convenience of the second, it needs to be defined as super, and it defines this element type. It's defined as an element type, and this key elite type. This is the component we use for calculations. This is the component used for our hash calculation. Define element type, then the key type, and this element type. This is our p pair. Obviously, when we retrieve the component, we are passing a t pair, right? So this pair, its key is our structure. So the structure is this. It's struct. Because this is a type pair. So in this place, it gives the UDQ's ID thing. So this place returns an F string. This is the one involved in the calculation. The one involved in the calculation. Value key, and when comparing this, it takes two values that participate in the calculation. Obviously, both passed in are CL subs, right? Clearly, they are all streams. Then, here in this one, is case sensitive. Then it determines if these two values participating in the calculation as criteria are equal, and this part is for the key term that we define separately and participate in the calculation. It performs a CRC catchem code. It's equivalent to generating a unique hash checksum code like this, right? Okay, we have finished looking at the whole thing. Then we look at this text below. Let me emphasize it one more time. Don't emphasize it. Let's just start writing. We can re-emphasize it when we write. Then f struct needs to have, it inherently has certain unique identifying attributes. Then we shouldn't use his root, etc. signs here, because we don't have the means to, we are for general purposes, and shouldn't specifically implement the equality of all these data. So we cannot do things like this, etc. Okay, because in this T-map, we just need their unique IDs to be equal. Then we assume they are equal, but in reality, when they are equal, we might need the incremental and complete attributes to be equal. Only then, within the game's logic, do we consider them to be equal. So we need to redefine a key function. Then, the key function that we define only relates to the unique ID. So, first, let's define the key function first. Clearly, this key function, it has a negative class. The negative class has two parameters. They are respectively the key init type and element init type. So, obviously, these two parameters, the first parameter is the key init type. Then, pay attention to this place. Don't confuse them under any circumstances. What he's saying here is actually a little confusing. Let me sort it out again. This is k type. K type is not the same as init type. Init type is fstream. P type is our struct. So, our value type, it is a template. Because your value can store a lot, can multiply an f string, can multiply other kinds of information. So this value type refers to here. It refers to here. This is the value type. This is the key type. This is a value type. And this element init type. It is this t part. It is this t pair. In this key init type, it is string. To emphasize again, this is element init. This is key init. And this is key type. This is value type. Then we continue looking down. So, in this place, we absolutely must not confuse it. Absolutely must not confuse it. Our FAD is when TeamPep is defined outside, passed in as the type of that value. Then we now define three net state functions for the KF. The first is returning this type. So obviously we take it from the tape pair, which is simply a ULIQUID. So we can just return the ULIQUID here. Okay. Let's look further down, and the first one is this. The second one is a comparison. So we pass two key init types for comparison. So for direct comparison, we use this. What we pass in is the init string. We can just compare the string type ourselves. And the hash in getK passes the k init type to calculate its CRC. Compute its hash. So now all conditions are met. Then we can discuss it and proceed with the implementation. Then there's something here that we haven't covered, which is called guide. A guide UID is something that generates a 32-bit number. We will demonstrate it to you shortly. You can do it right here. You can simply understand it as a unique ID. It's just a 32-bit hexadecimal number That will suffice. Next, let's take a look at how it is implemented. We first defined this temp, and this is key-type. It's the value type, and this is the class storage allocator, and this is our key function. We won't look at these two lines. This is the same as before, and this place specifies what we just defined. Then this value type is it. This value type, this is called key-type. So what is key-type? It is defined here. We define key-type as it, and then we initialize this spot. Two elements go in like this, and this one is constructed and their construction. The first passed floating point value, just construct an f-struct, and this struct is used as their k-type, and its value is 5. Then this uses 1, 2, 3f to construct an f-struct. Its value is 2. So you can see that it looks like this inside. This unique ID is generated within the constructor. You don't need to copy it externally, or you can write an external constructor to manually copy it. This spot automatically generates it by default. It's roughly equivalent to automatically generating an order number by default. Okay, I think you might be a little confused right now. Okay, let's write it out together again. We'll explain it as we go. Shall we first go back to our side? This is the most complicated thing. And second, this thing actually isn't. Maybe now the most common use for this is using this struct as when it's a component of a data table. This one is quite frequently used. When we discuss data-driven approaches later, we should cover this topic. First, the structure of ours, it might not like single reflection, so it didn't generate reflections. Then we won't generate them either. And regarding this part, we first need a unique ID. It isn't frill type. Actually, this unit ID should be private. Actually, it's best to be private. But we aren't very rigorous here. We don't worry about it either. This is a float. We can set this here. Personally, I prefer to generalize it, but you actually don't need to write this, because you will generalize it through the constructor. Okay, these irrelevant properties, you can write many. Then declare an explicit constructor here. After you declare it this way, when you write it, you won't be allowed to perform private conversions. So let me demonstrate it to everyone. What does this mean? So now I instantiated a structure. We will come back to look at this GUID later. Okay, so in this place, we write a function. This part must be explained to everyone in more detail. Otherwise, it will be confusing. Okay. Okay, if that's the case, we should paste it over here. That is to say, we have a struct. My struct, writing it like this one, well, you will find that, right? What if we do this? What if we remove this? I didn't notice. Let's remove this. Hey, it can do it now. This converts video for you. It converts it to film, video. It takes this. For example, this real one was just passed over, but we definitely don't want it converted to video. That would cause a problem. Okay. This is in C++. We skip over it. So at this point, we declare a structure. It looks like this. If you want to overload it, you can just reference what we wrote above. We won't overload it right now. Now, let's define this T function. First of all, it must be a template, right? Because the value type of this T-map can be various types. It is unrestricted. It's just this T-map. Its key value must be our structure. And then here, I declare this structure. So, at the same time, I need to inherit the base class. Inherit this base class. Inherit the base class. We pull it over here. Okay, after inheriting the base class, its first parameter is called element init type. The second parameter is called key init type. We will use this parameter to calculate the whole match and type hash, these things. Okay, then there's no problem. First, let's define our own compound class. We define it as our compound class. To make it easier for us to use later, we will also make a definition, that is, the element type parameter of the complex class and the init type of this complex class. This parameter defines it. We will map it to this projection. To make it easier for us to write our calculation functions later. And this function, the first is that we need to return which value, as the k-needed type of IARN at TTT5OT and TPIC to participate in the subsequent calculations. Obviously, we use the depir inside this LMD map. to make a determination using the unique optimized struct. Secondly, how do we determine if it is equal? It is already the K IT type, which is an effort here. Then we directly call the tau SAM method. We just need to compare if their scaling system is sensitive. And lastly, we'll pass this hash calculation over. This spot calculates using the CRC of this evidence. We can click into it to take a look. It seems like there are no comments here. It just calculates, right? Calculating a unique intersensor value. Use it as a differentiator. Okay, so our key functions are actually determined like that. We define two types and three state functions and make a call with it. Okay, so let's go back and talk about this. GUID. What is a GUID? It's just a globally unique identifier. Its properties are actually very simple, just making this ABC property. What is ABC? It's just a wintersent and it has a function you can pass in for utersent2 instances. It has a method called retain GOID. But this part is actually where we use. We can see the platform gate again. We created this spot randomly. Then all these four characters will undergo a random and finally combine them. It's this thing you get. Okay, so these few, and because using stream here is more convenient, we didn't use the GUID directly, so it converted into fstream. Then this is very simple, just tube stream. Then this place is where you make a simple open the best way. But this GUID is very useful. It has many formats. We can briefly go over the section for everyone. This class can be pulled out and explained separately. You can see, can it be imported? It can also be exported. And then it can, let's take a look. It can also parse it. It can also combine, right? The one we use the most is this. Actually, as for this GUID, the engine provides many classes similar to a GUID. For example, our fate tuple. This tuple temp class, these are all these kinds of. We use them very often. We will discuss them in detail later. Because this thing is quite frequently used. Sometimes when we perform network interactions, for example, if we work with a Flytek or Volcano engine, they require you to pass a painting ID. Then you can do it in this way, generate a GUID, and then pass it as a string. Because others do not know your GUID implementation, but others recognize this string. Okay, then we have defined it this way. Then we will use it next. How do we use it? We actually use it like this. So I can write this. So our first parameter serves as the key type for our tmap. The second parameter serves as the value type for our tmap. The third one is where this class stores the allocator. And then this is our key function. Also note that the value type of the key function must remain consistent. This is just the map to this sensor. Next, let's review what we have already implemented. Okay, there's an error here. It should be in one of our sections. This place is obviously missing a curly brace, right? Oh, the compilation is fine, right? So we can actually also store other types. Here you can see that it adds two elements, right? So we can store, for example, we can store a floating point value. We give it a float. Actually, if we use floating point values here, we can also store a structure. Actually, this value type doesn't really have many requirements or changes, as you can see in this place, right? Okay, we can just change this to float here. Then we should still interpolate this here. Okay, now I'll start it now. Then later, we can just set a breakpoint right here. Okay, my backhoe has been reached. Did you see this? This is it. Now it's empty. There are no problems at all. Let's pay attention to the local variables. Okay, here we just need to parameterize two elements. If you can see these two elements, you can look here. The first element's K unique ID and its auxiliary count and its integer. Okay, let's look at the second one. You can see here, look here, this unique ID. Its unique ID. It will regenerate every time it is constructed. Okay, this is Flutter. Actually, there isn't any problem. Okay, look at this float property. Let's take a look. This is this value type. Let's take a look. Oh, it's still int. I clicked the wrong one. It should be here. Yeah, hey, 20. Hey, this one. Look at these few. The unit ITs are actually all different. Is it okay? These two, top and bottom, are quite different. Okay, basically speaking, we'll just talk up to here. Okay, thank you everyone. This key function might be a bit difficult. If you don't fully understand it, then just try implementing it. You will naturally understand later on. And let me add some details here. It means that if the result of your match is equal, then they will return the same value from the hash. The same value from the hash. This is what it means. And if you modify the element state, it will change this function's result. Then you treat this kind of alteration as an undefined behavior. This way, the internal consistency will fail. So that means you have actually already solidified it. You've already put it in this map. So you shouldn't modify this thing. Because if you modify this thing, after you change it, it will no longer comply with its rules. It's like they've already done it, and then you change the result. When it tries to run, a problem will occur. This type of behavior is undefined. So this is quite dangerous. So it'll be like this. So just be careful about this in the end. Okay, we'll stop here.